Hi, my name is Patrik. I'm an applications engineer working at Wolfram math course, the developers of Wolfram SystemModeler. And, an applications engineer, you might ask, what do I do? Many believe I'm working with mobile apps. Well, that's not quite true. What I work is with this, I'm applying Wolfram SystemModeler and Mathematica within different applications, and one of those applications I'll talk with you here today is within the process industry. And before I start, I should say that many of the things I present here is partially funded by a strategic innovation program in Sweden that focuses on furthering the development of control software or software in general within the process industry and try to, move it towards Industry 4.0. So, for those of you who don't know, we generally define the process industry as something where we have a semi-continuous or even a continuous flow of production. Great examples of this is, for example, the beverage industries, the some food industries, chemicals, biofuels, medicines, and everywhere we have like a recipe for how you are supposed to do things. For example, you have a recipe where you make Coke and then you modify it slightly and add different ingredients, and then you get Sprite. I should say other beverages are available. So with these recipes, you input them into the process and you should be good to go, right? Well, not quite, because when you set up your process, you define, okay, this gets inputted and then we want Coke at the other end of it. But there will always be different process variations. So how do we account for this? Well, to account for this, we have to introduce the human element, and by that I mean the process operators, which are the kind of the cogwheels of the operation. And these are very important because you have a continuous flow of production and each one has their own station, and they need to know their stations in and out. They need to know, like, if something happens at their point in the process, they need to be able to solve problems in real time. And also it's very important because, due to the nature of the continuous flow, different stations will affect one another, because I'm doing something over here and then people down the line will be affected with how I solve different problems. And everyone if a problem occurs in the process, it could be, for example, we were talking about beverages. Suddenly the beverage flow is not as transparent as it used to be. Then you first need to, there are different ways to solve that problem, and how you solve that problem could be suboptimal in some cases. And I'll talk a bit about the process operators here, but for this I will use a running example. And the running example I will use is that of a large-scale paperboard manufacturer in Sweden. And the paper industry today is not doing quite as well as it used to do. But what they do here is they try to compete by having really, really high quality rather than high quantity. So let's introduce how a paper mill works. What we have is, let's put this a bit higher. What we have is a wood pulp, that you have wood pulp from, for example, pine trees, from birch trees, and you mix them together, with water, which comes down here. And the reason why you mix it with water is that you spread it out. You need to spread it out, the fibers in the pulp, evenly. And then you put it on to a drainage plate, almost, where you provide suction to drain the most of the water, and then you vaporize the excess waters in heated environments. And finally, you have some measurements of quality. And here is where we have different process operators in this process. And to really get the best kind of quality paper in the end, everyone has to know how their part of the production affects everything down the line. So each one of these, you can mixture with different quotas of fibers. You can mix in different amounts of water. You can provide different amount of suction here, and different heat here, and then everything there will culminate into a final measurement of quality in the end. And the quality I will focus mostly on today is that of grammage of the paper that comes out. It's basically the paper density, and what's most important is to have it even across the paper. So if you, for example, look at a newspaper and you look really, really closely, you'll see that there's quite a bit of variation in that paper. If you do like very high quality print, you need to have it very, very smooth. And everything that I just mentioned here goes into that quality measurement. And then there's also others, like you have to have optimal water content, optimal stretching. Well, you can actually look at one of these. I looked at this earlier, one of the schedules. You can see that this has very nice, actually very nice paper density, so you could get a feeling for what they're kind of striving for. I think they have a bit better, but maybe I'm biased. So this is one of the production plants where I was doing some consulting work. And let's go into okay, so we have the operators here. They are controlling the process. They're trying to get the best paper in the end. But what are the challenges they are facing here? So I listed some of the challenges they were facing. And one is, okay, so you got these operators. They've worked here for a very long time. They know their station in and out. But how did they acquire that knowledge? Well, they acquired it by working for a very long time. So if you get a newbie in there, you need to put him in charge of the operation, but you have this continuous flow where you can't just stop the machine and train them up. So you have these training manuals that says, okay, if you mix these fibers, it will kind of behave like this. But due to the nature of the continuous process, you have very high dynamics. I think it takes about 20 minutes from this point up there to this point down there, or maybe even more. It takes 40 minutes, actually. So things that people up there are doing will affect it very, very long down the line, and it's very hard to get that kind of feeling initially. Also, they got, in every process like this, it's not just this paper process, you get lots and lots of different measurements in upstream of the final quality measurement. For example, one example of this is the length of the fiber that comes from the input and then gets mixed with the water. So they measure the length of the fibers, but all the process operators there had a very hard time understanding what that signal even meant. So they installed a very, very expensive sensor, but then really couldn't do anything with the data that they got from it. And if these fiber lengths is something that it varies from hour to hour, day to day basis, or even, very much seasonal. And if you aren't the one who, because the operators can't affect these signals themselves, they have to learn by being there, looking at, okay, so this went up, what happened? But if it's happened on a seasonal basis, it's very hard to get that kind of dynamic knowledge of the signals they can't affect themselves. And this paper plant, for example, has a very, very high throughput. I think it's somewhere around 1 metric ton of paper every 3 minutes that comes down one of these lines. Then there's multiple of these lines. So you have the operators there that, something that they do within the time frame of 3 minutes will affect 1 metric ton of paper. And the reason why we started looking at this paper density variable especially was because this was one of the variables where the operator said, I have to be over there, at the same time I have to be over there, and adjust all these signals at the same time. It's just everything's moving too fast. And finally, this wasn't a problem for the operators, but for the higher-ups. They claimed that there were little to no cost consideration taken on the floor, whereby, for example, different fibers that enters this process costs different amount of money. And I think that pine is very expensive, and they have like this recycled paper that comes into the process that's almost free. But for the process operators, this wasn't really the aim of them to try and minimize the overall cost of the process, even though they had a very, very high input on how much the process costs in running every minute, depending on how they mix the different fibers. So we wanted to solve these problems using by first creating a model of the system. And the model that we created was based on, we have all these mass flows through the system, so we could create a physical model of that. All the equations for mass flows are very, very well known, but we also had the final quality measurement, the grammage deviation, and there's really not that much literature on how this particular paper plant would, how signals work. So what we did was we combined those physical models of the mass balance equations with entirely black box models that we had. We had 3 months worth of production data. We had minute data from 3 months, where we could track this grammage deviation over time. We could go back and see, okay, what did the operators change here? Why did the grammage go up? Why did it go down here? And we could, for example, narrow down. We had I think we had 200 of these signals, and we could narrow down which ones were the most important for the deviation output. And we also used step responses on those important variables. We tried and increased them a step, see what happened, and used multiple such experiments for both estimation and then some other data sets for validations of the model, and it fitted quite well. So the end result of that was a model developed in Modelica that looked like this. Now I want to demo this live at this model live. So in order not to confuse it with all these variables that the operators normally have, I brought a scaled down version that looked like this. And this is, if you remember the schematic I showed earlier, this is the fiber coming into the process. You have you mix them differently together, and that is a signal for the operators to use. Then you have some tanks that just where the mixing occurs, and you mix together some some water, and you have the drying sections, basically. So we created these models in SystemModeler, and then what we could do was we could use that to solve the problems that I previously mentioned. So one thing we did was here we have a training simulation for where you can interact in real time with the model. And what I'm going to show here is something that's built with Mathematica. But what you can do also is you can interact with these models in different ways. For example, you could use OPC, which is a standard communication platform within the process industry, or rather a protocol within the process industry. So you can get this all this simulation information directly in real time to a human-machine interface. You know, the normal places where the operators would interact with the process. So let me show you how this could look, and this is then built in Mathematica. So in the background right now, I'm running a real-time simulation of that model that I showed previously, and I reduced the number of the inputs here. But so you could see we could mess with the amount of fibers that goes into the system. We have 3 here. Normally there's much more. We can mix different amount of water. We can drain the system. So if I adjust one of the sliders here, you'll see that the system responds. And this is the real-time simulation that's running in the background. And of course, when you build a model, you can't capture all the variations. And so, for example, the fiber length that I mentioned previously, we can't predict the fiber length so that comes into the system. And what we could do then is we could estimate how large these process deviations normally are. So we could use this kind of interface to train new operators. I should say what this is. Actually, this is the grammage deviations that I've talked about very much, but haven't shown earlier. So we can track this in real time in a simulated environment. And this black line here would be, for example, the target, and they have different targets depending on different paper qualities. So to go back to the noise, to make it more realistic, you see that it's static now, but if we add some noise, it gets more into something that the operators would encounter in real life. So this could be something that they can use to train dynamics to operators for, let's see if it's actually, wasn't that much noise to begin with, but to train operators on how the system dynamics behaves. And this was well and good for the first problem that I mentioned, but it's still, and of course you can use it, you get a better understanding for the other problems. But we wanted to be able to help the operators, in the daily lives also, not just train new operators. So we took this one step further, and we said we have a model of the system. We can predict what happens if you do different inputs. So, for example, if I adjust this slider, what will happen? Well, we can predict what will happen in the future. And then we created a prediction environment. So I can start this here. We will see that this dotted line here shows where the process is heading given the estimated states. It's estimated because there is noise that the simulation don't know about, and given the current inputs. And if I change the inputs here, you'll see that it gets much, much easier to, I thought, right, I'm not really a process operator here, but they are much better at this than I am. All right, yeah. In any case, you could kind of get it to move. You can easier get it to move into the target area by knowing, okay, I changed this. How will it affect and you can do these predictions before you enter these input values. You can you don't have to commit to it. You can find, okay, I want to do this. Will it help the process? Okay, it won't. Then find something else to do. And now it's noise, so I have to change it continuously. Right, and this helps in some ways in all the signals they have. They get a better, because this takes into account the measured disturbance signals such as the fiber length. So this also helps them in that case. But we still have to solve the cost consideration. And I'm not going to go into every specifics of it, but and if someone wants to know more about how this works, please come down to please come and talk to me after this. But we implemented model predictive control, which is you take the model of the system you have, you make a discrete version of it, and you pose it as an optimization problem. So we could say, for example, that all right, it costs us this and this much to deviate from the target level, the target grammage deviation. And it costs us this and this much to use this fiber. And then suddenly you have an optimization problem that you can solve. And so we implemented that, and I can, let's see if I put on the, all right, I need to. So when I start this, it will, I told it can control every of these sliders. So I start this, and it will control these sliders for me. And now does that in real time, and it estimates the noise, and then in every time instant solves this optimization problem in order to keep as close to the reference as possible, given the cost of deviating from a reference, and also use the fiber. And here, I think I set the fiber number 3 to be the cheapest one. So it tends to use that if it's possible to get a good signal, even though you're using it. And I guess I can adjust the weights in real time. So I say, okay, now suddenly there's a problem. We're not getting in a pie, and this costs us very much. So let's just drag this up. So let's see if it's. So now it will stop using that. Okay, now this fiber here costs very much. Okay, then it stops using it and starts using the other ones. So the verdict was that we wanted to try this in different industries also, and because we realized that the same principles, they can be applied almost everywhere in the process industry. Everyone has these kinds of problems, the 4 problems that I mentioned, and one of the applications where we started applying it was the production of bioethanol, and there you put grain and mix it with water. At least in Sweden. Here in the US, I think you do it with maize. But in Sweden, you put a lot of cereal grain, water, and then enzymes, and then mix it together. So one problem they had was that the viscosity of the mixture was getting too high. The enzyme that they used to keep the viscosity down costs a lot of money. So there's a trade-off there. So one thing is to, you can learn the operators how these kinds of enzymes will affect the viscosity over time, and this is also a dynamic system. Enzyme kinetic breakdown takes some time before the resulting effect will be seen for the operators. So you can use the same kind of principles to train it. And we also, in lab scale, have applied this model predictive control, where we post an optimization problem for the controller to keep the enzymatic usage as low as possible while keeping the viscosity at an acceptable level. Right. Let's see. I'm really running out of time, but we have some other talks on SystemModeler. John had a talk yesterday on what we actually released a new version of SystemModeler yesterday, 2 days ago? Yesterday. So in case you missed that, come and talk to us and we would be happy to tell you a bit about what's new in SystemModeler. Also this talk here. And later in the day, me and John will give a presentation on how SystemModeler can be used in education. And it's kind of the same principles actually as the ones I showed here, where you get to interact with things in real time, and it gives you the intuition you need to really understand the system. And then tomorrow, Neil Singer here has a talk on how to rapidly prototype different systems. And he has a really cool demonstration down in the basement. You should check it out. It's a balancing plates. And I think you're going to talk a bit about it tomorrow also, apart from other things. And also a talk tomorrow on how fuel cells have been modeled in SystemModeler. And actually I should mention the demonstration I showed you here. When I'm down in the basement here, it is available. If you want to interact with these sliders yourself, you want to know a bit more about the system, learn how it works, learn about model predictive control, come and visit our booth down there, and I'll be happy to talk a bit more about it. So thank you.